So now, the second part is about the coordinates of any arbitrary vector b, which is not given by numbers here, just with its coordinates b1, b2, b3 as placeholders, okay? And always, if nothing else is given here, you should suppose that these coordinates are given with respect to the natural base, to the natural bases, which are the unit vectors along the Cartesian axes. So in other words, these are Cartesian coordinates, and whatever they are, but they are Cartesian coordinates. And now the question is how to convert them to the coordinates with respect to this valid basis A, which we just have shown to be valid. Okay, and now the question is, how do we do that? Okay, so it's almost the same thing with a little extension, because this time we write the following. We write down that, oh, sorry, sometimes pushing the wrong button because they are so small here. This time, where am I? Yeah. This time we write the same linear combination as before, x1 times a1 vector plus x2 times a2 vector, etc. But not is equal to 0 vector. This time it should be equal to vector b, any vector b, a given vector, but arbitrary. So why do I do this? It's because, by definition, the coordinates of a vector with respect to a given basis are exactly the scaling factors that have to be used inside the linear combination, which results to your given vector b. Okay, you see? It means that if I manage to find a unique representation of vector b by building this sort of linear combination using the basis vectors a1, a2, a3, these weighting factors, these scaling factors, x1 to x3 are, I could also have called them b1, b2, but that's dangerous because b1, 2, 3 have already been used for the Cartesian coordinates. But these are now the coordinates of vector b with respect to basis a. Now, we've already shown that, you see that I have the same coefficient matrix. If I would put this system of linear equations, I should just take the abbreviation SLE, okay? If I put this SLE in matrix form, I have exactly the same coefficient matrix as before. And we have just shown that this has determinant unequal to 0, so it has a unique solution. So that's an important prerequisite, of course, an important prerequisite for us to find a unique representation of vector b, but we have to find it. And so this is why I use the same procedure again, but not using zeros here, but using b1, b2, b3 instead. And then, it's a little plenty of work to replace these terms of b1, 2, 3 step by step. And then also this time we should better use Gauss-Jordan elimination to get to the complete final diagonal, or better, even better, to the unit matrix form, just to read our solution then on the right side. So that's what I'm doing. And you should not be surprised that, look at here, compare this one with this one, and this one with this one. It's exactly the same, instead of that, with the exception that from here on, I will proceed in order to get these two numbers also equal to 0. And then I have my diagonal form, and in the end, I have my solution. So that's what we're doing. And now it's a little more work to do. You see why? I have to subtract 2 times the working line from this row. So 2 times, but that's, on this side, we don't have anything to do because we've already done it, but we must look here, okay? So, because now, what do I have here? This is the working row, it stays as it is, but here I have to take this one minus 2 times this one, okay? So B2 minus 2 times B1, that's it. And then to eliminate here, I have just to subtract the working line, so it means also, now I switch here, B3 minus 1 times B1. So B3 minus B1. That's all for the first step. The first column has been eliminated. But now to the second, and as I told you, let's do it step by step. To eliminate here, we have to take this row times 3 and then add this one times 2. At this place, it means B1 times, now concentration is important, B1 times 3 plus, now look here, and I should have exchanged them so we don't get disoriented, you know, because B1 is put behind here, but just look carefully. So 3 times B1 plus 2 times this term. It means 3B1, 3 times B1. Oh, I must think about it. 3 times B1 plus 4 times B1, right? Is that right? Did I get it? This one times 3 times B1 plus 2 times this. So 3 times B1 plus 6. No, times 2 plus 4 times B1. I get 1 B1. And now I'm just wondering why I've written minus 2 times B1. Is this a mistake? No. I'm here. Okay. Something's wrong. Let me think. But I know that my result is correct. So anyway, help me. This times 3 and then adding this times 2. This is what we're doing, isn't it? So 3 times B1 plus 2 times this. 3 times, now I got it, sorry. 3 times B1 plus minus, sorry, 3 times B1 minus 4 times B1, and that's negative B1. I don't know why this happened. Okay, so it's negative B1, it's correct here, right? So next, but also plus 2 times this one, so plus 2 times B2. Now it's correct. It's not so easy this time if we have symbols to handle, okay? This one stays, it's the working row, and you see I just exchanged them so that they are in rising order, ascending order, okay? So it put minus 2B1 here to the left, and then plus B2 behind. Now it's done. This one, let's check it again. Times 3 minus this row times 2. So if I take this times 3, I have here at this place, I have minus 3B1, but then minus 2 times minus 2B1. So minus 3B1 plus 2B1. Minus 3B1 minus 3B1 plus, sorry, plus 4B1. Now I got it. Minus 3B1 plus 4B1 is in the end 1B1. So sorry, but now it's correct. So then there's no B2 here. So times 3, it doesn't matter. But then subtract 2 times this. It means I have to subtract 2 times B2. That's why I write minus 2B2. You help me. Look what I'm doing and tell me if I make a mistake. And I still have 3 times B3, but there is no B3 inside here. So 3 times B3 is all I get, plus 3 times B3. That's it, actually. Okay. So that's a little bit tricky. Anyway, we can proceed to the last position here. For good reasons, I did not divide by 4. Only very, very late in the process, as a last step, I would do this. Instead, now to eliminate here. So now we're done so far up to here. But now I do not do this. I could have left it away also, yeah. But anyway, from here on, I go to Gauss-Jordan elimination to eliminate these two. And that's the following. Here, I have to take this by 2 times 2, and then subtract the working row. So this times 2, yes, also here. 3 times 2 is 6. Okay, that's important. Here it is. Then 0 stays 0. That's nothing new, but 2 times 2 is 4 minus 4 equals 0. That's my elimination. And now 2 times this term minus this term. It's minus 2b1 minus b1. So this is in the end minus 3b1. That's correct, okay? Then 3 times 2b2 equals 6 times b2. And then subtracting minus 2b2. So I have, is that correct? No, I said it's wrong. I'm sorry. 2 times this one minus this one. 2 times 2b2 is 4b2. I'm sorry. And then minus 2b2. So 4b2 plus 2b2 is 6b2. It's really important to concentrate. Okay, then 2 times this no b3 here, and also but subtracting this. So subtracting 3b3 means minus 3b3. So it's really hard work. But then almost we have it. We have to take this one and take it by 4 and then subtracting this one. Now last time, okay, times 4. Minus 8b1 minus b1 is even minus 9b1. Then 4 times b2 times 4, 4 times b2 minus 2 times b2. 4 plus 2 equals 6. And that's why we get 6b2 again. Then no b3 here, but subtracting 3b3 also results to, to minus 3b3 in the second row. Here, minus 3b3. So that's it. You see, these two terms are equal and these two are equal by chance, by this procedure. So what do I have to do? Now you see this is diagonal form, but we want, even better, we want the unit matrix to be placed here. So that's easy. We just divide the whole row by 6, this one by minus 12, and this one by 4. That's what I've done. And then I get rational coefficients with the b's, but it's not so tragic. I think that's easy, okay? Divide by 6, minus 3, 6, and then reduce to shortest numbers, you get minus 1/2 b1, and so on. This gets a whole b2, this gets minus 3 by 6, then times b3, shortest numbers, minus 1/2 times b3, and so on. So in the end, you can control it. This is what we get. By the way, I hope you understand what it means in the end. So now you can use this as a conversion or transformation scheme for any vector b. If you just fill in its Cartesian components here, its Cartesian coordinates, and then you get its representation with respect to basis A, whatever it's good for. And I mean, it's just training, okay? So one example, simple example is if I take the 0 vector for b, I got 0, 0, 0 here, and everything gets 0 again. It just means that the two bases do not transform the 0 vector. The 0 vector is the same in any basis of R3. That's one important aspect. But for other values of b1, b2, b3, you get anything, okay? So that was in the first time, it was hard work. Okay, but we made it, and we should perhaps proceed shortly to the rest of it.